Hello everybody, in this video we will be using reinforcement learning to play Atari Breakout. We're going to be using Keras as a deep learning framework, and all the code would be written and executed in Google Colab. Breakout is the video game where a board moves along the bottom of the screen, returning a ball that will destroy the bricks at the top of the screen. The agent must learn to control the board by moving left and right, returning the ball and removing all the bricks. With reinforcement learning, we could try to make an agent that beats human-level performance in this game, given only raw pixels from the screen as an input, in order to maximize the score. We should definitely give a credit to the original paper by Volodymyr Mnich and Olaf DeepMind that is called Playing Atari with Deep Reinforcement Learning. There is also one more paper called Human Level Control through Deep Reinforcement Learning. All the links are in the description. Of course, it is possible to follow this tutorial on your computer, especially if you have a GPU, but I don't have one, so I will use Google Colab, that is a hosted Jupyter Notebook service that requires no setup to use, while providing access to computing resources including GPUs. By default, standard Colab profile is equipped with Tesla K80 GPUs, which are also okay, but for this task I decided to spend a few bucks on upgrading my profile to Colab Pro, which allows to use more powerful P100 GPUs. So let's dive into the code.
First, we need to change the runtime type of our Google Colab to use GPUs and also the high RAM. We're clicking Save and Connect to the server. Fine. So in order to make a reinforcement learning agent, we gotta go through 6 key things. The first thing to do is to install and import all the dependencies. We're going to be relying on Keras Deep Learning Framework and also Stable Baselines package that provides some useful wrappers for the environment, specifically Make Atari and Special DeepMind wrapper. Then we're going to examine our environment in order to get a clear understanding of what's going on, what are the observations that our agent going to be dealing with, what are the possible actions, and what is the reward function. So once we've done that, we're going to build up the model that is, in our case, would be a deep convolutional neural network, as we're dealing with pictures or images. Once we got our model built, we're then going to train it with the help of deep Q-learning algorithm. Then we're going to test it out and even make some cool videos of our agent really beating the environment. So first things first, let's go ahead and install and import all our dependencies.
So as I have already said, we're going to be using Stable Baselines package to import very important wrappers for the breakout environment. And also we need so-called Atari ROMs. Those ROMs are simply binary files that enable AIGM to actually run the specific game, like Breakout, for example, inside an environment class. So you can think of those ROMs as simply the rules of the specific game. Then I'm going to click Shift-Enter to run the cell and to install the dependency. Now we're gonna import all the dependencies that we have installed. So from Stable Baselines, we're gonna import Make Atari, method that simply creates the specific environment, and Wrap DeepMind wrapper that configures the environment the way it becomes much easier for our neural network to deal with. Like, for example, turning initial colored frames to grayscale, scaling them to a smaller size, and stacking 4 frames together in order to give our network the information about the dynamics of the environment, like, for example, the speed of the ball. We are also importing some basic packages like NumPy and Matplotlib, and also Keras for deep learning. From gem wrappers, we're gonna need a monitor to make a video of our agent play, and one more thing, we import drive from Google Colab. That is the package that allows us to save any files, specifically our model, to Google Drive. I personally find it very convenient that Colab is integrated with Google Disk, as this allows us to drop any files to our cloud storage directly from Colab. Alright, we're gonna run this cell and see that it gives us trace back. So no module named TensorFlow contrib. We're gonna see this file policy.py, and okay, this module right here, contrib, is the problem. And the problem is specifically that this module is not supported anymore, and all its content is moved to TensorFlow itself. So we're gonna delete contrib module right here, save this policies.py file, close it, and rerun the cell once again. Now it asks us to give permission to our Google Drive, and I'm totally okay with that. If by some reasons you are not, then it's okay. It's totally fine. You can delete this line right here. So it only enables us to save our model to the disk, but deleting it won't hurt the training process at all. We also gonna create the folder in Google Disk called G Drive. And okay, let's move on. Let's examine the breakout environment. First, states or observations. We call the function makeAtari and pass breakout no frame skip v4, that is the environment ID. So what is an environment? It's simply a class that implements all the methods for all kinds of interactions between an agent and an environment. For example, to get an initial state, we call environment.reset. Then we're going to print observation shape and show its image. So let's hit. Okay. We're gonna an observation shape is 210 by 160 by 3, where 3 denotes 3 channels for primary colors, red, green, and blue. So each element of this tensor is a color intensity that takes a value between 0 and 255. However, we don't need this level of detail in order to learn them. We're going to pre-process this image using wrap-deepmind wrapper. It implements all the pre-processing that is described in the initial paper. First of all, it resizes those frames to a smaller shape, specifically 84 by 84 shape. It crops unnecessary parts. It also converts the image to grayscale to make the channel's dimension kind of disappear, because we actually don't need the picture to be colored to learn our agent. We also normalize those values to be from 0 to 1 interval, as it is far more practical to have a normalized input when we are learning deep neural networks. There is also one more very important thing that is done inside this wrapper, is stacking 4 consecutive frames together. So why do we stack them? To give our neural network information about the dynamics of the environment, specifically the direction of the ball and the speed of the ball. Actually, the dynamics of environment is very important for our agent to decide what action to pick. So if you're looking at only one snapshot at a time, you're actually unable to tell where is the ball moving and what is the speed of the ball. So after the pre-processing that is what our agent gonna see. Next, we're gonna inspect possible actions. We run this get action meanings line, and we see that there are four possible actions. Either the agent does nothing, it can fire the ball, it can move the paddle to the right and to the left. So next thing is our rewards. So how do we get them? Environment class has the method env.step that takes an action as an input and returns next observation, reward, and the done variable. So what is the done variable? It's simply a binary variable taking true value when the agent misses the ball and loses 1 life. And by the rules of the game, our agent has 5 lives per 1 episode. So let's play random actions till the first time we miss the ball and plot the reward signal. So this time there was no reward. Fortunately, okay, this time we get this reward. So it turns out that at each time step we have either a reward of 0 or 1 when the ball hits the brick. Later on, we're going to plot that reward signal to control whether everything is fine with our agent receiving more and more actual reward in the process of learning. Okay, now let's move on to the network architecture.
In deep Q learning, a neural network should take a state as an input and return Q values for each possible action. You can think of this Q value of an action given the state as an estimate of future return that our agent gonna receive by picking this particular action in this particular state. The most common and suitable type of neural network that has to deal with images, and we have the sequence of images as an input, is of course convolutional neural network. Let's take a closer look on its architecture. The first layer is an input layer with shape 84 by 84 by 4 that totally corresponds with the pre-processed image that we have. It also has the fourth dimension, which is none. This means that that layer can receive data in batches. Those batches could be of any length, but whatever is the length of the batch, each element of this batch would be strictly an 84 by 84 by 4 tensor. The next layer is so-called 2D convolution. So if you're familiar with the concept of convolutional neural nets, it's very good. If not, that's okay. I'll try to give you an intuition with the help of this GIF. So imagine you have a 5 by 5 matrix, the one that is on the screen, and you have a 3 by 3 kernel or filter. So a convolution is simply a dot product between the initial matrix and the filter. This filter is sort of sliding through the matrix, and as a result we have smaller matrix, the so-called feature map. Here in this toy example, those weights in the filter are constant, but in our case we're going to be learning them to produce meaningful features for our neural network to make decision which action to take. For example, the resulting feature map will learn to take high value when a ball is in this particular region of the screen, and another feature map detecting the paddle, both of them giving information to the next layers to make the right decision upon what action to take in this combination of signals. So we're going to be using Keras layers module we imported previously, and specifically we're going to be using conv2d class, where 2D stands for 2 dimensions, as we're going to slide through the initial picture in 2 dimensions, vertically and horizontally. In order to use this conv2d class, we need to specify a whole bunch of parameters. First is the number of filters, which is in the first layer is 32. Each of them going to slide through the whole picture. Next parameter is kernel size, which is 8, meaning that a filter gonna be an 8 by 8 square. The next parameter is strides, which is 4. So if you think of the image being a square, 84 by 84, the filter being a smaller square, 8 by 8, sliding through a bigger one, the stride is how big of a step those filters take. In the first layer, stride is 4, meaning that those filters are going to move 4 steps in each of 2 directions. So the 4 steps to the right and 4 steps down. The final parameter is activation, which is in this case is ReLU. And it's quite easy to check that is the resulting output shape of the feature map is going to be. So if we slide through an 84 by 84 image with 8 by 8 filter with step of 4, we're going to end up with 20 by 20 feature map. And there are going to be 32 of them by the number of filters that we have. Then we're going to have 2 more convolutional layers stacked together with different filter sizes and different strides. The next is the flatten layer that takes all the weights of the final convolution and flatten them down to single column, which we're going to pass through a dense or a fully connected layer with a number of units 512. And the final layer is also a dense layer with a number of units equals to the number of actions. Note that the activation of the last layer is linear, as we want those 4 last units to have a meaning of actions Q values, and those Q values are real numbers representing the expected future return of the particular action being taken. So our model basically takes us from the image to an action prediction. Alright, let's build up a model with that function we wrote, createQModel. Well, actually, we're gonna build 2 models. The first one that represents our agent that is responsible for predicting Q values at each time step. The second one is the so-called target model. During the training loop that we're gonna see soon, we will be optimizing the loss between true Q values and our agent estimates of Q values. The purpose of the target model is to predict those true values. The target model itself is simply a copy of our agent that is made once in a while, say once in 10,000 steps. And although in the early stages of training it will fail to predict true values, but with more and more games played, with more reward being collected by our agent, the target model will eventually converge to true Q values. And the fact that we only update target model once in a while makes our loss function stable, and that is very important for a training process. I think that the most important part in structuring the neural network is to clearly understand the output and the input layers shapes. The simplest way to do it is by typing model.summary, and this is going to show you the entire model architecture. You see that we got our convolutional layers stacked together, and also our flattened layer and dense layers, and especially our dense layer with the 4 number of units denoting 4 actions. The total number of parameters that we need to learn is approximately 1.6 million, so it's large enough for us to use GPUs to train it. As you see, almost 90% of those parameters are in that dense layer. So convolutional layers are pretty lightweight, and that's why they are very effective. Now we're going to specify hyperparameters of our training and inspect the main training loop line by line. Stay tuned. The next part is to configure the hyperparameters for the whole setup. Before we dive into the hyperparameters, I'd like to share a link to Keras' official website, where you can see some cool examples of ML algorithms, including reinforcement learning. The following code with minor changes was taken from this site, and I highly encourage you to look it through. Okay, let's start with gamma. This is the discount factor for past rewards that is used to compute updated Q values. We will see it in the training loop in a few minutes. Next goes the epsilon, which is very important. So the epsilon defines how often our agent gonna take a completely random action. At the early stages of training, this parameter should be pretty high. In this experiment, we start from epsilon 1 and implement a piecewise linear decay. The first interval is from 1 to 0.2. the second from 0.2 to 0.1, and the last one from 0.1 to 0.02. So there will be 3 intervals, 1 million frames each, so 3 million frames total of epsilon decay. The next parameter is also very important. It's the maximum memory length. Or the length of so-called replay buffer, which was set to 190,000. So during training, our agent will receive observations from the environment, make actions according to the epsilon greedy policy, receive rewards, next observations. Those tuples of observation, action, reward, and next observation and done would be memorized in this replay buffer. And during training, we will take random batches out of this buffer with a batch size of 32. So hopefully during training there will be more and more tuples with positive reward, which will allow our network to recognize what actions were better and to assign more Q value on them. Large replay buffer helps training, but even with high RAM option in Colab, you may run into memory issues, so adjust memory length to your hardware capabilities. We set maximum steps for episode to 10,000 to guarantee that the episode will not last forever, as this is quite possible in Breakout when the agent hits the ball, but the ball doesn't hit bricks. It could really be an infinite process. So in order to avoid this, we set max steps per episode. We will perform the actual optimization of loss function with respect to the parameters of our neural network every 20 frames. We can do it more often, but that can harm the stability of training process. A target network will be updated every 10,000 frames. This is also done to make targets more stable, and we will use Adam optimizer with learning rate of 0.00025 and a Huber loss function. That's all for the hyperparameters. We're now ready to dive into the most complicated and interesting part, the training loop. Let's go on ahead. Training loop. The first thing to do is to create empty lists to collect history of our training process. Those are the lists for actions, states, next states, rewards, and done. Those 5 lists make up our replay buffer. The main evaluation metric of our agent is the mean reward per episode. So we're gonna create one more list to gather episodic rewards. We set running reward to 0. That will be computed later as the mean of episode reward to check the condition for solving the task. Episode count and frame count are so to count episodes and frames respectively, as we will have several conditions on them during training. We start our training loop with resetting the environment to get the initial state. By the way, we operate with already pre-processed environment, and we set the episode reward to 0. We're going to run this loop until the task is solved. So the next for loop, we go through each time step within one single episode. We increase the frame count by 1, and with this code snippet, we make our action selection. If frame count is less than 50,000, which is epsilon random frames, or epsilon is more than uniform random value, we take completely random action. We do this by np.random.choice. Otherwise, we convert the state to tensor. With tf convert to tensor, add up one more dimension. To feed the modal input layer shape, we feed this tensor to our modal to get Q values, and we pick the action that delivers the highest Q value computed by our model. After that, we decrease our epsilon by a little bit with the decay rule that I described earlier, and we apply the selected action to our environment by running environment.step. With this line here, we get the next state, the reward, and done parameters. We convert the next state to NP array, and we add up the instant reward to the episodic reward. We save everything to our replay buffer and change the variable state to the next state. Next if condition is actually the heart of our reinforcement learning algorithm. We initialize the training every 20th frame. With this line here, we sample random indices of the batch size length. With the help of those indices, we're going to sample observations from the replay buffer. Now, here we do this. And now, that is the point where actual reinforcement learning begins. We get updated Q values as rewards plus gamma multiplied by future rewards that we get from our target modal in this line here out of next state sample. We also set the updated Q values to -1 if it is the last frame of the episode. To compute Q values, in order to calculate loss between Q values and target Q values, we implement this one hot mask. So for the reason that updated Q values or target Q values are computed with respect to the next states that we achieve by picking certain actions during our training process, we only need to compute loss for the Q values corresponding to the actions that have been really taken. So with the help of our agent model, we compute Q values out of state samples, and we apply this mask to get only Q values for the action that were really taken. We name that variable Q action. Then we calculate the loss, which is the Huber loss, between Q actions and updated Q values. So we do all this within the gradient tape method. That is a special method for recording operations for automatic differentiation in TensorFlow. So we have completed the forward pass with this code snippet. Then we need to do the back propagation. We do this by calling tape.gradient, and we pass our loss and modal trainable variables to compute gradients. And finally, we call our Adam optimizer to get new weights for our neural network, and this is done by simply calling the apply gradient method. All right, we got the hardest part done. Now over here we get our target modal weights renewed every once in 10,000 frames. Then we're gonna print the log of the training, which includes running rewards, episodes count, frame count, epsilon, and loss. We update the replay buffer by deleting the very first observations, and we compute the running reward to check the condition for solving. For the purpose of this video, we'll end the loop when running rewards hits 18. That is already a pretty high level, and I bet very few of you can beat that. Okay, let's run it and see whether everything is okay in this part. So we see that running reward is really low on this stage of training. Epsilon is very high, and that's because our agent is sort of exploring the environment, making random actions, trying to get positive reward signal. So we're gonna let this train for several hours. With the GPUs I have, each will take approximately 10 to 12 hours to train. So see you in a while. So after approximately 10 hours of training on GPU, we can observe the results. You can see that for a pretty long time, the running reward stays really low, but eventually it increases as our agent explores the environment and starts to gather more and more rewards. See that epsilon is also decreasing, and the agent begins to exploit the knowledge about the environment that it has learned. By the frame count of 3 million, it finally reaches the minimum epsilon of 0.02, and with this small rate of exploration it continues to increase the running reward until it hits the average score of 18. So it took our agent more than 30,000 episodes to solve the task. The next part of our tutorial is saving and loading the model. Now I'm going to show you how you can save the model you have trained to the Google Drive. It's done simply by choosing the path, which is content/G drive-my drive-models. We have already created this path. We type the model name, which is Breakout Model 1, and we save the whole model to this path by simply calling model.savePath. This line of code here saves the entire model with all the weights and all the architecture. You can see it in this left panel over here, the contents of your Google Drive, and you can really see that the model has been saved to the path that we have chosen. Models, breakout model, and here are all the contents that we need. You can load the previously trained model with this line tf.keras.models.loadModel. So I just leave it here with comment, so feel yourself free to use it when you need it. Alright, let's move on to the final part of this tutorial where we will make videos of our agent play. This is the final part of our tutorial where we will be making videos of our agent play. In order to do this, we will be using gym.wrappers.monitor. This is the wrapper that allows us to create videos. We only need to specify the environment, which is breakout, no frame skip, and still we're using wrap DeepMind wrapper to preprocess. And we got to specify the folder for the videos. As usual, we reset the environment to get the initial observation, and we also create some auxiliary lists and variables to keep track of the playing process. We got to be playing one single episode of 4,000 timeframes max, and we got to be using epsilon greedy policy with very small epsilon of 0.0001. But if our agent is stuck not receiving rewards for more than 200 timeframes, then we're going to be slightly increasing the epsilon in order to get out of this vicious circle and to continue getting the reward. So this is the code snippet for some plots where we're going to see the reward signal and the epsilon for us just to keep track of the playing process. And when our agent loses all its lives, we're going to break the loop and reset the environment. Okay, I'll just run it. Oh, beautiful. And in this left panel over here, we got this photo video. So now I just simply download all these videos and we gonna watch them. So this is the resulting video of our agent play. As you can see, our agent is doing pretty well with the ball moving at a low speed and is also capable of adjusting the movements of the paddle as the ball speed increases when it hits more distant layers of bricks. The most wonderful part of all this is to see how the agent digs a tunnel around the side of the wall, allowing the ball to be sent around the back to destroy a large number of bricks, which in the original paper is considered to be the optimal strategy. So that's all for this video. Hope you managed to achieve good score in Breakout with the help of reinforcement learning. Please let me know in the comments whether you managed to destroy all the bricks. The learning process is really time consuming, but with proper hyperparameters and powerful GPUs, it's quite possible to get good results within 10 to 12 hours of training. Hope you liked this video and I wish you good luck in reinforcement learning. Goodbye.